Welcome back to another Physics 7 video lecture. This one's going to be on Newton's laws. I'm going to try to keep it short and sweet this week. Last week we went a little over time. So what I'm going to do is just lay them out there. We're going to talk through each of Newton's laws. I'm going to express to you how you've seen them before and how the versions we're going to present, the kinematic versions is what I'm calling them, how the versions of Newton's law that we're about to present are slightly different. Yeah, and then that'll be that. We'll go through a couple intuition builders and wrap up quick. All right, let's hop in. So, Lecture 7, Newton's laws. In the introduction, all I want to do is remind you of the definitions of momentum and then express Newton's laws in two forms. So, we'll have a couple of equations, some of them you've seen, some of them you probably haven't. And we're going to spend the rest of the lecture showing how the things that you know are equivalent to the things you don't know yet, the things you haven't written down yet. Okay, so let's talk about momentum. First of all, I know we've been talking about this for weeks now, but just so we have it clear, like written down in our heads, momentum is a property of a particle or of a system of particles, of a collection of particles. So if some object has a mass m and a velocity v, this vector here, the momentum is just the velocity scaled by the mass. Okay, similarly, we've just spent a little while now talking about angular momentum. So angular momentum referring to some object that has a moment of inertia I, or a rotational inertia I, traveling at some angular velocity omega. The angular momentum L of this system is just given by I times omega. So it's the rate of change of the angle, so how quickly it's rotating, scaled by the moment of inertia, which is analogous to mass. It's a measure of like how hard it is to make the thing speed up or slow down. Okay, so Newton's laws, we've seen them before. So we've seen them before in the form of these three equations. So we've seen them as a statement of conservation of momentum. The change in momentum of a closed system is 0. So if there are no net external forces acting on a system, then its total momentum will not change as a function of time. That's the first law. In words, one way I might say this is to say that objects in motion stay in motion at the same velocity unless acted on by an external force. So force, another way to say that is that force drives changes in velocity. Nothing else drives change in velocity besides force. So a velocity will stay the same unless an object is acted on by an external force. The second law is that the change in momentum is given by force times time. So force is the thing that changes momentum. We kind of established that in talking about this first law. Force is the thing that changes momentum, and it changes it over time. So if I have a force that's acting for longer, I've got a greater change in momentum. This tells me the scaling, the rule for scaling between force and change in momentum. It tells me how quickly or how much force affects momentum. This lets me translate from a known force and a known time duration to a change in momentum. Okay, it tells me the nature of changes in momentum. That's probably the best way to say that. All right, and then the third law is that every change in momentum must be met with an opposite change in momentum. This is one we've touched on briefly, but roughly it has to do with the fact that if two objects are interacting with one another, the change in momentum of one must be met by a change in momentum of the other. This is really a restatement of the first law. That's how I think of it, is that if I've got multiple members of a system and they interact with one another, if I have, say, a two-member system and they interact with one another, any change in momentum, oops, I should put a negative sign here, sorry about that. Any change in momentum that one of them experiences is going to be reflected by a change in momentum elsewhere in the system, in the opposite direction. That's to conserve the total momentum, so that the total momentum of the combined system changes in that total momentum sum to 0. Or another way of saying that is that the total momentum of the system is constant. So the changes summing to 0, the total momentum being constant, those are equivalent. Okay, so here's the new stuff. The new stuff is what I'm going to call this, so these three, the three laws that we've kind of already seen before, I'm going to call these the momentum laws. So the momentum-based Newton's laws. This is one translation, if you like, of Newton's laws. The ones we're going to try to translate to over the course of this lecture are what I'm calling the kinematic laws, the kinematic lens of viewing Newton's laws. So I'll rewrite them and then state them. I know I've written them there as well, but just to kind of give a little bit of my narrative on top. Oops, that's the first law. Here we go. The kinematic lens, the first law is that the change in velocity of a closed system is zero. In particular, so if I want to get really specific, then what I would say is that the change in velocity of the center of mass for a system is zero. So what that means is, like, if I've got some collection of particles that's moving around all over the place, well, there's an average position of the mass, and that average position of mass moves along at a constant rate. If I have a single particle, what it says is that my mass moves along at a constant rate as long as there's no external forces on it. So there's like the single particle interpretation of this law and the multi-particle interpretation of this law. Typically, it's stated as the single particle one. So the velocity of a particle is constant as long as there are no external forces. Change in velocity is zero. Okay. The second law says that the net force, any net force acting on a member of a system, any force that is not balanced by other forces, say, so a total force, the sum of all the forces acting on the particle, that's the net force. So the net force is the sum of all forces. The net force acting on a particle drives that particle's acceleration, and it drives that acceleration at a rate that is, inversely proportional to the mass. So the heavier the object, the more slowly the acceleration for a given force, the more slow the acceleration. Acceleration represents a change in velocity. So force, change in velocity, looks a lot like this one, right? And we'll break it down to make it a little bit more explicit soon. There's a force on one side, there's an acceleration which has to do kind of with speed, it's a change in speed per time, and a mass, which we know momentum has something to do with mass. That'll be one of the easier ones to show. The third law says that forces that act from one object on another object are mirrored by a force that acts on the second object by the first object. So the way you say this in words, the common like physics statement that gets blown out of proportion all over the place is that forces come in equal and opposite pairs, or for every action there's an equal and opposite reaction. Those are the words that people often use to describe this law. What it means, we'll get into in a little bit more detail in a minute, but what it means briefly is that any force that one member of a system exerts on another member of a system is reflected as a force that is exerted by the target on the source. So I've got two bodies, and I'll make them different colors. I've got two bodies, and one of my bodies exerts a force on the other body. Let's say this is gravitation, so it's like the Earth and the Moon. The other body, the one on the right, exerts a force on the first body that is equal and opposite. So these two vectors are equal in size and opposite in direction. That's all this law says. And we'll dig into that a little bit more in, I think, the fourth part of this video lecture. Okay, so these are our statements we'd like to prove. These are the Newton's laws, the kinematic version of Newton's laws. This is a new lens through which to view momentum conservation and understandings of how momentum changes as a function of force and time. So what I'm going to do in the next 3 videos is I'm going to talk about how we go from this understanding to this understanding, why hopefully it'll make sense and we can port our intuitions about momentum over to this kinematic form of Newton's laws. And then at the end, we will wrap up and go through some examples. All right, see you there.